In this video, we're going to learn about mole ratios. There's two types of mole ratios that we use fairly regularly in chemistry. One is between different elements within a molecule, and the other is between different molecules in a chemical reaction. So when we write out a chemical formula, we usually have this format of some element followed by a subscript with the number of atoms of that element, followed by another element and its number of atoms. So an example here is butane, where we have carbon and hydrogen in our molecule. And my hydrogen and carbon element symbols tell me that. The amount I have of each is in the subscript. So I have 4 carbon atoms and 10 hydrogen atoms. And this 4 to 10 is really the mole ratio of carbon to hydrogen. So if I were to think, how many carbon atoms do I have relative to hydrogen? It would be 4 carbon to every 10 hydrogen. And we use this when building Lewis dot structures and trying to decide what this molecule looks like, and it really defines that chemical identity of the molecule. So we can use these in calculations where we need to know maybe just the number of carbon atoms in a sample of a certain mass, or we need to know the number of hydrogen atoms. But other than that, the version of mole ratios that we typically use the most is going to be the coefficients in a balanced chemical reaction. So coming back, though, to our mole ratios within molecules, if I had 5 molecules of butane, and I really wanted to know about that number of carbon atoms, I would multiply it by my ratio of 4 carbon atoms, that came from that subscript, for every 1 molecule of my butane. I could write out a conversion factor that's 1, okay, let's do this, 1C4H10 equals 4 carbons, which also equals 10 hydrogens. From this, I could build a lot of different conversion factors. I could have 4 carbon atoms for every 10 hydrogen, or I could have the one that relates carbon to the number of molecules, or I could do that for hydrogen too. And this can help with a variety of different types of problem-solving scenarios that you might encounter. So looking at chemical equations, we use coefficients to determine or to communicate how many of each different type of molecule will be required to make the products from our reaction. So if we had that butane again, but now we had it undergo a combustion reaction, it would react with oxygen to form carbon dioxide and water. And if we balance this equation, we'll get 2 butane molecules will react with 13 oxygen molecules to form 8 carbon dioxide and 10 water molecules. And so from this, we could create, if we wanted to know about the number of moles of oxygen that would react with our butane, we could create a conversion factor from these coefficients that stated 2 moles of our C4H10 would equal 13 moles of our oxygen. And then we can use this conversion factor to go in between the number of moles of butane we have and the number of moles of oxygen that are required to react with it. And so I'm putting, in this case, I'm setting up this coefficient, or sorry, setting up this conversion factor. So my moles of butane are on the bottom, so these will actually cancel out with the 1 mole of butane I was starting with. And then that 13 moles of oxygen come on top, and these units don't cancel out, and instead those become my final units. And this highlights why I suggest that you always write the chemical formula after the unit moles, to give context to the unit of a mole, because we'll have, in many cases, conversion factors that are going from the mole of one type of molecule to another. And so my units in all of these different steps here, or the conversion factor and my starting and my final answer, are all mole. And if I didn't have these chemical formula to say which the mole was, it'd be really hard to decide if I needed to multiply by 13 over 2, or if I needed to multiply over 2 over 13 to solve this problem. So we use this to predict the amount of a product that will form, or if we know the amount of product, predict the amount of a reactant that reacted. And this is really a powerful tool in chemistry because it allows us to make and follow recipes, essentially. And similar to giving units and following a recipe for a chemical reaction, when you're baking, usually when you look at a recipe, it tells you what to expect for your product. My cookie recipe always says it'll make typically 3 batches of a dozen cookies, or 36 cookies. So that way I know to multiply my entire recipe by 2 if I have 60 people coming over. Similarly, stoichiometry allows us, and using mole-to-mole conversions allows us to predict the amount of a product that will form. So that way we can determine exactly how much of our starting materials to use to create what we need. So in this case, we're given some information about our oxygen. We have 0.25 moles of oxygen gas, and it reacts with an excess of oxygen. So let's take a look at this problem that utilizes mole ratios to predict the amount of a product. So there is a typo in the lecture notes, my apologies. But if we start with 25 moles of oxygen and we let it react with an excess of hydrogen, how many moles of water will we form? So we want to know how much water forms when we combust oxygen and hydrogen together. And the only real piece of information we've been given is that we have 0.25 moles of oxygen. So that's going to be my starting point. I'm going to need to convert then to units of moles of water, because that's what my question is identifying the goal to be. So to be able to do this, I need a conversion factor that goes from moles of oxygen to moles of hydrogen. I'm actually going to write my units into my conversion factor right now before I even determine what the numeric values are. So that way I know that I'm going to multiply it by the right version of the ratio. So I want to end up with moles of water, and I want to cancel out units of moles of oxygen. So moles of oxygen will be at the bottom. Now, coming to my chemical reaction that's balanced, I can use the coefficients to create conversion factors. So in this case, 2 moles of hydrogen will react with 1 mole of oxygen to form 2 moles of water. And I can use this conversion factor to solve a lot of problems. And it disappeared. The one we're going to use is that we have 1 mole of oxygen is equal to 2 moles of water. And again, these are just coming from the coefficients. When there's no coefficient, it's really a coefficient of 1. And now I'm going to come in and put these into my actual problem. So I'll have 1 on the bottom of my conversion factor and 2 on the top. And when I multiply my 0.25 times 2, I'll get 0.50 moles of water that form. Give these problems a try, and we will review them in a following video.